we have a standing wave like del 2y by del x square, that is equals to 1 by v square del 2y by del dt. So let's say this one is my equation first. Okay. So if you want to write this equation, like we can write y equals to a e to the power I, and then we can write kx minus omega t. So where k is your wave number and omega is the angular frequency. That clear? So let's say I am assuming this is the equation second. And from de Broglie hypothesis we know what? So the lambda can be written as your 2 pi by h by p, right? Lambda can be written as your h by p. Okay. Now, if you know these things, we have lambda equals to h by p, and we know the value of wave number that can be written as 2 pi by lambda. Now, if I substitute this value of lambda here, then what you will get 2 pi divided by h by p. And again, this equation can be rearranged, and that can be written as x divided by 2 pi. And finally, you will be getting this is p divided by h square. So finally, we have calculated the value of wave number, that is equals to p divided by h square. This is one parameter that we have calculated that will need while substituting this equation second. Next is that from photoelectric effect, we know that the value of energy E, that is equals to, we can write it h nu, right? So this can be also written as h divided by 2 pi, and then we can multiply this by 2 pi. So h divided by 2 pi I can write h square, and 2 pi will be omega. So from here we can calculate the value of omega, that is equals to E divided by h. Right? So basically what we have calculated the value of k, we have calculated the value of omega, and let's try to substitute the value of k and omega in equation second, and we will obtain this value in that form. Let's try to understand this thing. So from here we will be getting the value y, that is equals to a e to the power I, and in place of k I can write the value is p divided by h square x, minus in place of omega I can write e divided by h square t. Is that clear? Okay, so now y can be written as a e to the power I divided by h square, and obviously px minus e. So let's say this is my equation third. Now this is the wave equation that corresponds to the function of x and time t. Is that clear? Okay. So now from this equation particularly, I'll try to do the first order derivative and second order derivative of this wave function, and we'll try to derive the Schrodinger equation. So let's see how we can do this. So if I do the first order derivative of del y, and this y can be written as psi of xt, because in quantum mechanics we use wave function notation as psi of xt, and that can be written as a e to the power I divided by h square, and then that can be written as px minus pt. Right? So let's say I am doing this is my equation 4. Now if I do the derivative of psi with respect to x, first order derivative, it can be like a I divided by h square, and then if I do the derivative, this will be p, and then again it can be written as I divided by h square, we will get it px minus et. And if you see a into e to the power I px minus et, that is basically psi. So finally you will be left with del psi by del t, that is equal to a I by h square p psi. Right? So let's say this is my equation 5. We will get del psi by del x, that is equal to I divided by h square p, and then psi. Is that clear? We will see So I'll assume this is my equation 5th. Okay. Now again, if I do the second derivative of del psi by del x, so I can say that del 2 psi by del x square, and that will give you the value. If I do the derivative of this things again psi, so it will be del psi by del x, and we know the value of del psi by del x from here. So directly I'll write here that minus it will be your p square divided by x square, and that will give you the value of psi. Is that clear? So now let's try to understand that is I square is 1, right? So this will be like that. So from here we can calculate the value of p square psi, that will be equals to minus h square del 2 psi by del x square. So I'll assume this equation is my equation 6. Okay. Now next is that we have the wave equation psi of xt, that is equals to a to the power I by h squared and your px minus et. So if you do derivative of this with respect to time, you will be getting a, and obviously I divided by h squared, and if you do derivative of this, you will be getting the value minus e. It will get multiplied here, and then you will be getting e to the power obviously I divided by h squared and then dx minus et. So finally here you will be left with del psi by del t, that is equals to what? A and e to the power I by h squared dx minus et, that will give you the value of psi. So finally you will be left with minus I e by h squared psi. Is that clear? So next I can rearrange that equation again and see what kind of equation we will get further. So if you rearrange that thing, so you will be getting minus h squared divided by I del psi by del t, that is equal to e psi. Okay. So if I multiply and divide in the numerator and denominator by I, so it will give you I h squared divided by IH so here I think I have done mistake. I square is there, then I square minus 1. So there will be minus 1 that side. Okay, great. So that will be IH, and then here del psi by del t, right? That you will be getting that value is e psi. Okay. So let's say I'll assume this one is my equation 7. Okay. Now these were the some assumptions that Schrodinger took in order to derive this Schrodinger equation. So now the second this assumption was it should follow the conservation of energy. So if I want to write total energy, that can be written as your kinetic energy plus your potential energy. Kinetic energy plus potential energy, right? So total energy I write as E, that will be kinetic energy, can be written as P squared divided by 2m plus potential energy is V. So if I multiply this equation, let's say this is my equation 8. If I multiply equation 8 with psi, so it will give you the value E psi, that is equals to P square psi divided by 2m plus V psi. Is that clear? Okay, so now we got the value of E psi, we have the value of P square psi from equation 6 and equation 7, and then we will substitute this in equation 9 and see what will I get. So if you substitute this value of E psi over here, so that will give you the value of IH del psi by del t, and that is equals to P square. We have got the value that is equals to minus I h squared divided by 2m del 2 psi by del x square. Is that clear? I h square del psi by del x, something like that, and plus b psi. So because p square by 2 and value p, the value of p square psi we got is p square psi, that was equals to minus I h del 2 psi by del x square, and this value I have substituted here, and finally p square psi, that was equals to minus h square del 2 psi by del x square, right? So now here we will substitute the value of p square psi in equation 9 and e psi in equation 9, and we will get the value of like I psi I h square del psi by del t, that is equal to, we can say here that minus h square divided by 2m del 2 psi by del x square plus v psi, right? So now we are able to derive the Schrodinger equation that I have already written earlier. So this is called as the Schrodinger equation. Let's say I am assuming this one is equation 10, right? So we are able to derive the Schrodinger equation using the classical wave equation or standing wave equation now. So next, what we have to do here, so we will be solving this equation, because it is, if you will see, this equation is a second order partial differential equation, linear partial differential equation, where psi is a function of x and time. And in order to solve this, we will use separation of variable techniques to solve the PDEs, and then we will be able to break this particular problem in two different ODEs. And solving ODEs will be very easy. Once we will substitute the boundary condition, we will be able to get the value of psi and t, psi in terms of x and time. So what we will do here, so here I will assume psi of xt, this psi, that will be a function of, explicit function of psi and psi of x and phi of t. This Schrodinger equation, let's say I h square del psi by del t, that is equals to minus h square divided by 2m del 2 psi by del x square plus v psi. Is that clear? So here you will see that this psi that you can see here over the screen, that is a function of x and t, and I assume this is small psi of x and phi of t. Now we have broken this capital psi in terms of two functions, explicit function of x and t, right? Now once we will substitute this in the above equation, let's say this one was our equation 10. So see what will I get. So I can write this as I psi del psi into phi, right, by del t, that is equals to minus h square divided by 2m del 2 psi into phi divided by del x square plus v psi into phi. Is that clear? So here what we see that small psi and phi is an explicit function of x and t. So in this differential, because phi is a function of t only, so psi will be treated as constant. Here phi is a function of t, so phi will be treated as constant with respect to x, so phi will come out of the differential. So directly we can say, why we can write here that psi I h, now it can be directly written as now d phi by dt, right? And here psi is a function of x, so phi will be taken as out of the differential, so that will be minus h square divided by 2m and then phi. This can be written as del 2 psi by del x square plus v psi into phi. It's as simple as that. So now we'll see here, we'll divide this above equation by phi and psi both sides. So what will I get here? You will be getting 1 upon phi I expect 1 upon phi d phi by dt, that is equals to minus h square divided by 2m into 1 upon psi d2 psi by dx square plus v. Is that clear? So let's say this one is my equation 11. Okay. So if these two derivative has to be equal. So both of these parts should be equal to be a constant. Then only it can be equal to. So now what we have seen here, we have broken down the partial differential equation into the ordinary differential equation, where phi is a function of explicit function of time and psi is an explicit function of space. So now I can explicitly write these things as I h squared by phi d phi by dt, that is equal to constant. Let's say this one is my equation 12, and then I can write this as minus h squared divided by 2m 1 upon psi d2 psi by dx square plus v, that is equal to constant. So let's say this is my equation 12. So basically what you can see here, we have two ordinary differential equation. From first equation we will get the value of phi, and that will give you the time varying part of the wave function. From second equation, that is equation 12, we will solve the value of psi, and we will get the spatial variation of wave function. So we'll start solving this equation 12 and 13 separately, and we'll see how we can get the value of phi and psi. And then finally we can combine both of these solutions in order to get the complete wave function, which will be a function of x and time. So in this lecture I will be solving only equation 12 and see what will I get. So here you can say that I h squared, I think there was I h squared divided by phi, and obviously your d phi by dt equals to c. So you can write here this thing as d phi by dt, that is equals to 1 upon phi d phi by dt, that can be written as your 1 upon I h squared c. And if you multiply and divide this by I, so you can write here d phi by dt, that is equals to minus I by h squared c. So directly you will get the equation of this ODE, that is phi equals to, let's say I am assuming a is a constant and e to the power minus I by h ct. Is that clear? So we have got the solution for the time varying part of the wave function, right? So I will stop the class here. In the next class I will start discussion about the spatial varying part, that is the equation 13, and we will then finally combine with phi and psi to get the final wave function, that will be a function of x and t. Okay, thank you.